So right now you guys are expert in calculating where is the sun at any point, and those charts that we have seen basically show one clear message, and that is in the winter the sun doesn't really go that high. In Tulsa, Oklahoma, the sun will never go to 90 degrees. Actually, it will never even go to say 85 degrees or 70 degrees. The sun will go a little bit low and come down. But in the summer, the sun will go really high. And so if you are adjusting the tilt angle of a PV panel sitting on the highway 75, obviously it's clear what azimuth angle should we set the solar panel at. South. It has to be facing south, because half the day the radiation is coming from the east and the other half it's coming from the south. So the panel need to be facing south. And if one of you should basically jump on me right now and say, wait a minute, it's usually a little bit hot, warmer in the afternoon than in the summer. Are you telling me that it's the same radiation coming from 9 a.m. the same as 3 p.m.? Yes, it's the same radiation coming. It's just that we feel warmer because the ground get warm and the building get warm and they radiate themselves, right? So then you feel at 3 p.m. different from 9 a.m. But as far as the radiation coming from the sky, it's symmetric, right? So as far as the solar panel sitting in the highway is concerned, I better be facing south. Okay? However, the PV, I have small power solar light in my yard, and I don't let them face south. They are all basically facing northeast. Why? Every one of them has like a tiny panel like this. Okay? And they have battery in them, they charge all day long, and then basically when the light goes off, they turn power themselves off. I got them from Lowe's basically. But I don't set them facing south. Why? Why don't make them face south? That's not bad. East. It's because they only get the sun from morning until noon, because after noon they are in the shadow of the house, because they are sitting in the front yard. So their day is really just from 9 until 12. So they need to get all the sun radiation during that time. And after that, basically they are in the dark anyway. So I optimize them so that they are in the middle of their own day, not the full day. Okay? The second part is so we adjust the solar azimuth angle, or the plate azimuth angle. It should be facing south if we have the whole day. So if you have it on the highway, he'll have the whole day, unless there is a building or a tree blocking him. Then there is no point in that part. But the second part is the tilt angle of the plate. Should we set that plate at what angle? Should we make him horizontally or vertical or 45 degree or what? So normal is the right word. Normal to what? Normal to the sun angle, right? So obviously that will be different during the season. So during the winter you want the panel to be a little bit facing to the ground, and in the summer you want them to go back as if they are almost horizontal. So you want to tilt back in the summer and you want to tilt forward in the winter. So if you can go to the roof every single month and adjust the angle, good for you. But people don't. And so you, and on the highway also, they just want to leave the sign all year long without fixing it. So there is optimum for every month, but there is also optimum for all year long. And they figure out that the optimum, and I will show you the table and it will prove to you that the optimum for all year long is latitude tilt. So Mother Nature is so kind to us. I mean, you don't have to remember that many numbers. Latitude tilt. What is latitude tilt? what is the latitude of your city? Set the angle at that number and you will be good all year long. Yes, you will suffer in the winter and you are not going to get as much as you should get in the summer, but at the end of the year, if you calculate how many kilowatt joules that you capture during the whole year, you are best in that position. Of course, ideally, you go and adjust every single month, right? So what is our latitude in Tulsa, Oklahoma? 36. So we should set it at 36. So if you are lucky and your roof at 36, perfect. Just let them lay flat on the roof at 36. If your roof is not at 36 but at 50, then maybe you need to tilt them back a little bit, right? So you can adjust them on the roof to get the right angle. And again, if you are for all year long capturing, it's 36. But maybe you are not really for all year long, but you are worried that in the winter this thing will suck. So I am really, and in the summer I am over designed anyway, so you may want to optimize for the weakest link. You may want to optimize for the winter, right? And then basically say, we will get extra in the summer, what's bad about this? But at least I'm not gonna be running out of energy in the winter, right? Very good. So here is the radiation that they get in what? This is 48 north, and this chart is 48 north. So 48 north, that's not Tulsa, Oklahoma. Tulsa is 36. 48, that's a little bit what, Michigan kind of thing. So what is, this is the time, and this is the months. And again, optimize, this is just one day, that's the average of the months. So one thing we recognize is that there is a bunch of zeros over here and bunch of zeros over there. What is that? That is their winter. So in the winter, you don't get radiation at 5 a.m. But in the summer, you start accumulating radiation from 5 a.m., not even 6. At 5 a.m. you are still collecting, because the sun comes early in the summer, right? You also notice the symmetry, right, between the months, and you notice that there's two numbers, always two numbers, okay, and those numbers are normal and horizontal, okay. So what is normal radiation? Normal radiation is someone having the collector like this, normal to the sun beam. The sun go and he's doing this. This is basically those mirrors. So those mirrors always tracking the sun, they will get the normal radiation. Okay? Although those are not exactly normal to the sun, they have to sit with an angle between the sun and the tower so that they reflect to the tower. But what I'm trying to explain is that if you track the sun all the time, you get the normal radiation, and that's obviously much higher than the horizontal radiation. What's horizontal radiation? That's the parking lot. How much radiation is falling on the parking lot? How much radiation is falling on a flat roof building? A lot of industrial plants just have a flat roof, and that's what they will get. Okay? So you can see like 79 and 54. Look at this, 500 over here, 79 over here. Because that's early, in the early time in sunrise, the horizontal will hardly get anything. The normal will get everything, right? And then during the day, that balance will drop a little bit. Especially during the summer. I guess in the winter the angle is really low, but you go to the summer and you see the difference shrink between the normal radiation and the horizontal radiation. Okay. Interesting, in all this thing, the maximum over here is like 900 watt per meter square. And we said one sun is 1000 watt per meter square. So the people living there, if they buy a solar panel from Lowe's that say 160 or 200 watt or 300 watt, they are guaranteed they will never get it, right? Because they will never be able to provide one sun on the panel, right? Very good. So So one level of question is find out the sun. The second level, and we find the sun by calculating alpha and AS. But my really favorite questions, and the thing that really practical to ask about is, what is the optimum angle for my solar panel on top of my RV when I am basically having a trip in the whatever national park we go to. So what would be the optimum angle of your plate? Let's say you went to Grand Canyon and it's due September 21st, and it's 3 p.m. and you would like to basically get it to work maximum power so that you can charge your device and stuff. So what would be the optimum AS? Sorry, what's the optimum A for the plate, and what's the optimum tilt for the plate at that particular hour, at that particular day, at that particular location? Let's start with the A. So what is the A? The plate or the collector azimuth angle. Just like the sun angle with the south is the solar azimuth angle, the plate angle with the south is also called the plate azimuth angle. So what would be the optimum plate azimuth angle? If you want to set it to a number, what would you set that angle to? No, that's here if it's only at noon, right? See, we are trying to optimize it for exactly 3 p.m. in the Grand Canyon on September 21st. What should be my optimum angle, azimuth angle for the plate? No, who said that the sun is going to be there? What your answer should be is, find out where is the sun, find out the azimuth angle of the sun at 3 p.m. 3 p.m. our angle doesn't mean the azimuth angle is 45. We said that, right? You have to calculate AS for the sun. And so let's calculate AS for the sun, and let's say it turned out to be 27 degrees. So the sun is 27 degrees with the south. Where should we orient our plate to? 27, right? Wherever the sun is, make the plate face the sun. Now the tilt angle of the plate, we will calculate the other angle, the solar altitude angle, alpha, and it turned out that at that time alpha is 50 degrees. What should be the plate tilt angle? If the sun is making altitude angle 50 degrees, the plate tilt angle should be if the solar altitude angle is 50 degrees, the sun is making 50 degrees with the horizontal, what should be the tilt angle of the plate? If the plate tilt angle is 0, he's laying flat. If the plate tilt angle is 90 degrees, he's vertical wall. No, think again. 40, so that what happened? They are normal to each other. So radiation of the sun is making 50, the plate should be 40. So then they will have 90 degrees between each other. Right? Those are the two angles that you need to optimize the plate on hourly. Of course, if you said let's leave it all year long or all day long, that's a different question. But if you are adjusting it hourly, you find out where the sun, you adjust the azimuth angle to the same as the solar azimuth angle, and you adjust the tilt angle to be 90 minus alpha. Okay? Right. This part about how the radiation that we get is two parts. We said that direct and diffuse. Right? Watt per meter square and watt per meter square. And if the plate is not optimized to be normal to the sun, so the plate is just like someone sitting over there, and you're trying to figure out, well, how much he will actually generate. I wish he was facing the sun with exactly 90 minus the alpha. Then he will get what? If you do this, then he will get the normal radiation. You just open the chart for that location, that particular month, that particular hour, and if it's say 833, he will get the 833. But what if he's not at the right angle, or he's facing a little bit off? You know, the sun is at south at noon, but he's facing northeast. Or alpha is 50, but his tilt angle is 10. What should you do? And so what should you do is this. You need to find out how much. So if this is the sun over here, and this is the normal radiation, this is the 833 that we get from the table. That's how much his normal radiation is. The plate will get only component of this guy, and that component depends on the angle between the normal direction and the normal to the plate. The plate also has a normal to it, and the angle between them is called the incident angle, theta I, and that angle is not in our textbook. And so you need to write this equation in the back of your cover in pencil in case you want to sell your book later on. But this equation is important to calculate what is the angle between the plate, the normal of the plate, and the beam, the sun beam. Because it's this angle, it's the cosine of this angle that represents the fraction that we will get. So cosine theta I is sine alpha, cosine beta. What's beta? This is the first time we see this. Beta is the tilt angle of the plate. So if beta is 0, he's flat on the wall, on the floor. If beta is 90 degree, he's a vertical wall. Okay, beta 45, he's basically, halfway. Cosine alpha, sine beta, cosine gamma minus gamma s, and that's confusing. What is gamma and gamma minus s? It's actually A and AS. It's just the textbook where this equation came from. They don't call the azimuth angle A and AS. They call it gamma and gamma s. Gamma S for AS, solar azimuth angle, and gamma for A, the plate basically azimuth angle. Alright? So then what? So once I calculate this cosine theta I, then I multiply cosine theta I by the radiation coming from the sun, and that will be the part falling on my plate. Okay? So obviously if theta I is 0, cosine theta I will be 1, and you will get the whole radiation. And for theta I to be 0, how would that is possible? Theta I will be 0 if the plate is normal to the sun. Right? If the tilt is exactly 90 minus alpha. And you can try to do this. If you set the tilt angle to be exactly 90 minus alpha, you will find out that cosine theta I will be exactly 0. Of course, starting with gamma and gamma s, or A and AS are the same, right? So if you set gamma equal gamma s, that cosine will be 1, and if you set beta to be 90 minus alpha, you will immediately realize that cosine theta I is going to be 1 and theta I is 0. For other scenarios, just calculate the theta I and take the fraction of it. And that example will finish by this example. That example exactly trying to do this. He's trying to calculate cosine theta I, multiply by the normal radiation, and say that multiplication is how much I'm going to get on my plate. So let's read. So he said a normal beam of radiation, I normal, has a flux of 350 watt per meter square. That's what they are getting, 350 watt per meter square. What is the flux reaching a solar surface facing due south? So his azimuth angle is, a plate facing south, his azimuth angle is 0, right? And tilted south by 25. Okay, so he's tilted south by 25. So his tilt angle is 25. So beta is 25. At 11 a.m., and assuming 11 a.m. solar time, not standard time, so we don't have to do this long correction. 11 a.m., that means our angle is minus 15. Every hour, 15 degree. On the summer solstice, so that means delta is 23 plus 23.45. I don't even need to use the equation for delta S. At 40 degree north latitude, so L is plus 42. So he gave you all the angle. All you have to do is say basically cosine theta I, use that equation that we just wrote in the back of our book, get cosine theta I. So here is the solution. He figured out, well, then theta I is 15.5, And so how much of the 350 will I get? 350 times cosine 15.5. He will get 337 falling on his plate. This is a fraction of the normal radiation that he will get. Is that clear? So this chapter is all about three angles really. Alpha AS and theta I. Okay, and in order to calculate those three angles, alpha and AS and theta I, you need three other angles. Latitude, that's your location. Delta S, that's the date, the solar declination angle, and the hour angle, HS, which is the time converted into degrees. That hour angle, if he give you solar time, it's piece of cake. If he give you the standard time, it's a whole new problem with more equations to turn the standard time to solar time. Alright, questions? Alright, very good.